Hi guys, so we're gonna watch a video on 7.2. Again, I'm doing it on the piece of paper here and I'll just be kind of voicing over. We'll discuss tomorrow if you like this method of videoing or if you prefer kind of watching me write things up on the board. So 7.2, some really important formula comes into play that are all on your AP Stats formula sheet, so no stress there. But some kind of important things here. Let me see if I can get a little closer. Great. All right, so P is an unbiased estimator of P hat, right? So we now know if something's unbiased, right, we know that the mean of the sampling distribution is going to be equal to the true center. So this is the end I'm going to do some exploration around how they knew this, and then I'll go ahead and give you the kind of final formula. So how we knew this, P hat, right, we know it's like if you wanted to find the proportion of successes, right, you do all the numbers of successes. So there were 17 oranges out of the total, right? That would be the true proportion of orange M&Ms in the container. Okay. Well, we know from binomial data, right, that this is a binomial situation, right? You either have orange chips in your orange M&Ms or not. Well, we know that the mean for binomials is n times p. So if we're going to go ahead and do our little formula here, we're going to do our n times p. If we did, let's go ahead and call x is going to be 1. So our n is going to be n times 1 over n times p. We just left over with p. So we know that the mean of the sampling distribution should be equal to the true parameter. Okay. So we're just equal to the true parameter. Sorry, this is n times c. Yeah. So the final thing is if it's an unbiased estimator, we know the mean of the sampling distribution should be equal to the true parameter. Same thing about the spread, right? We know that the standard deviation formula for binomial situations is the square root of n times p times 1 minus p. Okay. And we're going to go ahead and kind of do the same exploration. So the standard deviation of the sampling distribution will be 1 over n, right, times that p, and that's going to be that same kind of formula here, which is going to go ahead and equal the same thing as if we kind of brought the n in as an n squared, right? To bring this guy in, we can make it an n squared. Again, you don't need to know the derivation of how we got this, but we need to know the final formula. We see that one of those cancel out, and we're left over with the standard deviation of a sampling distribution will always be p times 1 minus p over n. If you go ahead to your formula sheet here, right, you're going to see that this is what we have for proportions. When we're talking about sampling distributions, the mean of the sampling distribution will be equal to the true parameter's mean, if it's unbiased. And we know that the standard deviation of the sampling distribution will be equal to the square root of p, 1 minus p, divided by n. Awesome. We know from here, right, as we've proven before, as n increases, right, think about as the denominator gets bigger, right, the standard deviation will get smaller, right? We know that as true to be fact, right? As our n gets bigger, think about the denominator is getting bigger, this number will get smaller. Great. The distribution of p hat will have the same shape as the distribution of the binomial random variable x, right? So it's all stemming from the binomial random variables that we were talking about last chapter. The normal approximation of p hat. As n increases, the sampling distribution of p hat becomes approximately normal. We saw that multiple times, right, that our distributions always ended up normal, right? All of our sampling distributions ended up in a normal shape. So there's a few conditions around that we've already talked about, but we're going to check those again. The conditions that we're always going to have to check when we're doing a sampling distribution are the following. N times p has to be greater than 10. N times 1 minus p has to be greater than 10. They're the same conditions as the binomial random variable ones that we had talked about before. This proves that a distribution is normal, or approximately normal. We'll write that. So any time that we're going to use these formulas, we always have to check these conditions first. This whole second semester of stats is going to be checking conditions. And so we'll come up with all these things that we have to check before we can actually do the problem. The last condition is that the n, big N, or the population, needs to be at least 10 times bigger than the sample size. So this is saying your sample can't be the majority of your population, right? It can't be more than 10% of your population. And this is the rule that we need to check, and it's often called the 10% condition. And this we'll always have to check before calculating the standard deviation. So these two, before we ever use these formulas, we have to check that first that this is going to be approximately normal distribution, and that this condition that the population has to be 10 times bigger than 10 times the sample size, the 10% condition, in order to check to make sure the standard deviation will work. So find the mean of a sampling distribution p hat is, we write the mean of the sampling distribution will always be the true parameter if it's unbiased. And the standard deviation of the sampling distribution is going to have it been the square root of p times 1 minus p all over n. Notice this is p, not p hat. This is the true proportion in here. So we see as the simple random sample size n increases, the standard deviation will decrease. Okay? So those are going to be our important formulas. So let's go ahead and try a problem with it now. So we have about 75% of young adults, internet users 18 to 29, watch online YouTube videos. Suppose that the sample survey conducts a simple random sample of 1,000 young adults, okay, and calculates the proportion p hat in the sample distribution who watch the online videos. What is the mean of the sampling distribution? Okay, well, we know that the mean of the sampling distribution should just go ahead and be equal to the true proportion. Well, the true proportion in this case is 0.75. Right? There's our p, our parameter, and here's our n. Great. Now it says find the standard deviation of the sampling distribution p hat. Check that the 10% condition is met. Great. So we know that anytime we're doing a standard deviation, we have to check that the population, big N, is 10 times the sample size. So the population in this case are all young adult internet users. Is that greater than 10 times 1,000? Yes, I think that there's more than 10,000 young adults in the US or even in the whole world, obviously. And so now we can go ahead and find our standard deviation of p hat. We go ahead and use our standard deviation formula, p times 1 minus p all over n. And these two formulas are right on your formula sheet. Feel free to kind of simplify this down to make your life a little bit easier. So what I always like to do is I like to multiply this first, so 0.75 times 0.25. Simplify that top part first, kind of makes your life a little easier. So let's see, 0.75 times 0.25, square root 0.1875 over 1,000. And then I go ahead and check what that is going to be. So square root of 0.1875 divided by 1,000. Boom, there's my standard deviation for this distribution. I'll round that to 7 there. Okay, great. So we have our mean, 0.75, our standard deviation, 0.0317. Now we got to check to make sure the distribution is normal. So before we are able to do any problems, we got to check that it's normal. So we check our two normal conditions. Our n times p has to be greater than 10, and our n times 1 minus p has to be greater than 10. So let's go ahead and check. 1,000 times 0.75 greater than 10, check. 1,000 times 1 minus 0.75 or 0.25 is bigger than 10, check. So the normal conditions are met. Great. This next question is asking, what if we made a sample size as 9,000, if we increase n to 9,000 instead of being 10,000? How would that change the sampling distribution of p hat? Well, we know that if we look at our standard deviation formula, as n increases, the standard deviation is going to decrease. So, as n increases, the standard deviation would decrease. Last thing, what would happen to the sample? What sample size would be required? So we're looking for an n to reduce the standard deviation to be 1/3 the value that you found above. Okay, so 1/3 of the value that I found above is 1/3 of my standard deviation. So let's go ahead and calculate that. We got 0.00, and I'm gonna round to 4/6. Great. And it's saying, what would the n have to be? So I'm gonna set that equal to my standard deviation formula. So we still have our same p times 1 minus p, and we're trying to solve for n. Okay. So I'm saying we're using the standard deviation formula here for p hat, and we're plugging in everything except for n. So to first solve this, I'm going to kind of go up over here. First thing we want to do to get n alone, probably square both sides. Now I never actually square this number because it ends up being really small and kind of hard to follow. So I leave that written as 0.0046. Squared, we know that, and then we're left over with this. We know from 0.75 times 1.75 was that 0.1875, so I'm just gonna write that there over n. Great, we have an n on the bottom though, and we're trying to solve for n. So I probably am gonna cross multiply. This is the most algebra you're gonna see in this class. And then go ahead and divide in order to get n alone. So we're solving for n because it's asking what would the sample size have to be. So lastly, I'm going to say, okay, well then 0.1875 divided by 0.0046 squared. All right, let's see what we got there. We have 8, 8, 6, and so since we always are going to have to round up when it comes to people, right? We're always rounding up when it comes to people, so I make it a 2. So again, this was saying, what would the sample size have to be if we wanted to make this 1/3 this size? So we found what's 1/3 of the standard deviation we had gotten, and then we plugged in our p, and we had to solve for n. So first we had to get rid of the square root by squaring both sides. We then could cross multiply to bring the n up, divide, and there's our answer. Always rounding up because we're dealing with people. So that's one type of problem that we're going to see when using these sampling distributions. Always checking our conditions and kind of using our formulas there. Okay. Looking for the second question here. So let's go through example 2 now. Uh-oh. Sorry, 1 second here. I can't find example 2. All right, quick pause and we'll go through example 2 here. All right, here we are again. So example 2 is saying the superintendent at a large school district wants to know what's the proportion of middle school students in their district are planning to attend a 4-year college. Okay. Suppose that 80% of all middle school students in her district attend college. Okay, so that's our true parameter. What is the probability that a simple random sample of size 125 would result in a 7 percentage points of the true value? Wow, there's a lot of information here. I'm given a p, I'm given an n, but it's asking what is the probability? What is the probability? Well, we know we can use our probability rules like binomials. Could do that. Or we know that we can find probabilities out by finding this value, right? Going from data to z and then z here, right? There is our probability of something happening. How likely something has happened to find our percentile of the probability there. So because we know that we can prove that these distributions are normal, we then can go ahead and use normal CDF. So that's going to be our goal. We're going to prove that these things are normal. Then we're going to go ahead and set up a normal CDF problem just like we know. So the mean of our sampling distribution, we know if it's unbiased is always equal to p. So my mean in this distribution, 0.80. My standard deviation in this distribution, we can go ahead and use our standard deviation formula, 0.80 times 1 minus 0.80 all over n. All right, so we have our mean and standard deviation. Go ahead and plug that into your calculator, and we go ahead and get a standard deviation of 0.0357.